I'm Mike Schnecker. Part of electromagnetic compatibility, or EMC testing, is the testing of conducted emissions. Conducted emissions, unlike radiated emissions, are not transmitted through the air, but rather are conducted on the power lines of the device under test. Conducted emissions are usually measured at a lower frequency range, up to 30 megahertz. And just like EMI testing, as part of all of EMC testing, need to be tested in a certified laboratory for certification. However, during the design process, it's not difficult to measure conducted emissions right on the bench using an oscilloscope. We're going to show how that's done in this video. So right here I have a Rohde & Schwarz RTE 1104 oscilloscope. And what we've set up is a switch mode power supply, which is shown right here in the middle. We've connected that to a load on the right here, and we've connected the input of the switch mode power supply, this DC to DC converter in the middle, to a line impedance stabilization network, or LISN. This is a custom LISN, which is designed particularly for this application, which provides DC in, DC out. And a LISN basically is a device that presents a fixed known load to the input of the device under test and allows you to tap any voltages riding on top of the power signal into a measurement device, in this case an oscilloscope. LISNs are available in standard form for line inputs for standard voltages, for example 120 volts in North America or 240 in Europe, and various other different voltages around the world. Those things are standard parts that can be purchased from Rohde & Schwarz. In this case, we're going to use a DC converter with a 12 volt input, a 10 volt input into the LISN, and then we're going to be driving the power supply with that input. And using the LISN to tap the voltage off, we're going to measure it. And so what we see on the oscilloscope screen here is the voltage that is superimposed on the input lines to the switch mode DC to DC converter. And you can see that, as typically you'll see, is these spikes associated with the switching action of the regulator and the ripple overall on the voltage that's superimposed. What we're interested in seeing for compliance of conducted emissions, however, is usually in the frequency domain. So what we really want to see is the spectrum of this signal. So what I'm going to do is I'm going to turn on an FFT. Using the toolbar on the top here, I'll select the FFT tool, and then I will touch the waveform so that I can enable the FFT. So here on the bottom we have a spectrum, and we want to adjust the spectrum so that it covers the range of interest, in this case 150 kilohertz to 30 megahertz. So we'll enter into the setup screen for the FFT. We'll select a start frequency of 150 kilohertz and a stop frequency of 30 megahertz. And a resolution bandwidth per the standard is 9 kilohertz. So we're going to select 9 kilohertz for the resolution bandwidth. And so now we have this spectrum set up to cover the band required for conducted emissions. Now finally, the display is normally done in a log frequency scale. So we want to scale the frequency domain, that is the horizontal axis, in a log scale. So we're going to select frequency axis from linear and go to logarithmic. And then finally, we measure the amplitude of these signals in terms of dB microvolts. So we're going to want to set the vertical scale to dB microvolts, so we're measuring in the right units again for this type of compliance test. So we're going to select units, and we're going to select dB microvolts. And so now we should see a spectrum down here in the lower display that shows dB microvolts versus frequency on a log-log scale, which is exactly what we want to see. Now there's one more thing we need to do before we can test this number against the standard, and that is we need to count for the coupling in the line impedance stabilization network. So the LISN taps a percentage or a portion of the waveform off of the main signal, and so we need to know we need to adjust the gain of the oscilloscope to compensate for that. Now, this particular LISN has an 11 dB insertion ratio, which is part of the design of the thing. So we're going to enter that into the channel menu. So I'm going to select channel 1 here, and on the probe setup, I'm going to enter the gain factor of minus 11 dB here. So we'll compensate for that. So put 11 minus 11 dB. So now we have the right scaling for this signal. And once we've adjusted that level, you can see the upper waveform, which is the voltage versus time, has gotten smaller while we've compensated for the gain. So we need to readjust the vertical gain of the oscilloscope so that it reads the proper calibrated amplitude in millivolts in this case. And so now you can see the spectrum here, dB microvolts, starting from 150 kilohertz out to 30 megahertz on a log scale. Now, in order to find out if we're compatible with whatever standard we're trying to meet, we want to put in a compliance mask on the frequency domain display so that we can see where the amplitude of the various frequency components fall relative to that mask. And so we can store compliance masks right on the instrument, and so I did store one in here for this particular standard. So we select from the mask menu test definition, and then we'll open the mask associated with the standard we want to test. In this case, it's EN 55022 for quasi-peak. And then we've opened that mask, and we'll just close this window. And here you can see the compliance mask above the waveform. And to make it a little bit easier to see, we can just minimize the channel 1 waveform. And so now we're looking at the compliance mask above here, the measured voltage on the input of my switch mode power supply. And you can see that the mask is actually showing up in gray, and you can see this one harmonic, the lowest frequency one, is just below the mask at the lowest frequency. If I was designing this part, I'd probably be a little bit more concerned about that because it's awfully close to the compliance mask. So I might want to do something to try to reduce those harmonics that are very close to the mask. And this is really the essence of designing for EMC, finding those areas where you might potentially fail and fixing them earlier on in the design process rather than waiting until you fail a test, a very expensive test at a calibrated facility. So that's a very quick EMC test that you can do for conducted emissions using a Rohde & Schwarz oscilloscope and a simple lab setup.